Hello students, I'm going to talk now about impedance, first from a general point of view and then to specify sort of how it can be thought of in terms of transistors. So today we're going to talk about impedance. Now the main issue when it comes to impedance, which I think is confusing, is that impedance itself as a concept is used in both loose senses and more restricted or more specific or more precise senses. In the most precise sense, basically it is the combination of resistance and reactance. Basically, this involves resistors, and this involves inductors and capacitors. In the loose sense, however, it's really the sense that we tend to think about it in terms of the electronics class. In a general sense, it is the sort of overall response of a circuit to an applied voltage and finding an applied current. So I have an overall response which I can write as delta V over delta I to any sort of change. So if I have a delta V and I want a delta I, that gives me my impedance associated with that circuit. So let's remind ourselves what we're talking about with regard to equivalent circuits. So it's very important to understand this concept with regard to the equivalent circuits. That's where it really comes home. So let me change my pen. So I can use the concept of impedance in the context of equivalent circuits. And the equivalent circuits that we're interested in are the Thevenin equivalents. So if I think of any circuit, usually what I want to know is what is its Thevenin equivalent, which means I want to know that if I given some circuit and it has some output, then I want to find its equivalent in terms of a model that has a voltage source, which I'll call V0 or V Thevenin, and some internal impedance, which I'm going to call a resistance, R Thevenin, but it could also be a more complex object called Z Thevenin, which has both reactance as well as resistance associated with it. But for the most part, these are the same. We don't have to keep changing our mind between one and the other unless we're worried about frequency. So make sure that you're clear on this. I'm taking some unknown and I'm going to make it equal to something that I'm going to try to analyze. In terms of inputs, it looks the same. That is, if I have another kind of a circuit here and it has an input, usually drawn on the left side, I'm going to think of it in terms of its Thevenin equivalent too. But for the most part, if I think of a Thevenin equivalent of an input, usually V0 is equal to 0. That is, we don't typically have inputs of circuits that we really make that have some non-zero input voltage already on the input. It usually is applied from the output of some other device. But otherwise, there's no distinction between this resistance in terms of how it acts with the outside world and this resistance over here in terms of how it acts with the outside world. So I usually call this, R Thevenin, the output resistance or output impedance. So I'm going to change that here to Z out or Z R out, and this is R in. So there's nothing fundamentally different between input resistances and output resistances other than the fact that they're connected with inputs in this case or outputs in this case. Okay. So let's move on and see if we can understand how to relate this model, or this model, with this basic overall response definition. So we'll draw an example looking for Z out or R out. So I have my equivalent model, and I'm going to model it as some V out in series with some Z out. I'll put a box here to make sure that this is as most general as I can. Sorry for the sloppiness. And I'm going to ask the question, how do I think about this quantity here? Well, if I want to know the output impedance of this device, what I would do is I would add some test load. So this would be some test load, R test. And I'm going to ask the question, what is the value of Z out that provides a particular voltage across R test for different values of R test? Another way to write this is to say, let there be some loop equation, and I will write it as follows. V out minus the current times Z out minus the current times RT must be equal to 0 by Kirchhoff's loop rule. Now I will ask the question, what is the voltage on the output? The voltage on the output here is simply equal to the current times RT. So that means that V naught minus I Z out is equal to V out. So if I make a measurement of V out, and I also make a measurement of the current that flows through it, I can then determine the output impedance. So what I'm going to say is, let's assume that V naught is constant. And I'm going to vary V out, so that takes it over to a delta V out, and I want to find a change in I out. So if I take my equation here, what this says is that delta V naught, which is going to be basically equal to 0, minus delta I Z out is equal to delta V out. Just taking the differential of this equation right there. So this produces the result that delta V out divided by delta I out with a minus sign is actually equal to Z out. So this then becomes the equation that I want to solve. That is, I want to find this and this for a given setup. That is, I want to know what is this quantity given this, or what is this quantity given this for a given setup. That allows me to find this quantity. In a very similar way, you can calculate the input impedance based upon some applied voltage on the output and looking on the current that flows through. For example, if I set up another equivalent, which I'll do as follows. Here's another equivalent. I'm going to say that this has some input impedance, Z in, and I am going to apply some delta V on the input, and I'm going to get a delta I. And by the loop equation, I have V in minus I in times Z in must be equal to 0. And so it's very easy to see that Z in is given by delta V in divided by delta I in. Okay, so that's the second one. Now you notice, going back to this first one, there's a minus sign here, but there is not a minus sign in this one. So that's all you really need to know in terms of the definitions. Then you can apply them to particular situations. So I'm going to stop this video here, and if you want, pick it up on the next one, which has to do with transistors.